Good morning everyone. I am Jeyachandran J, Assistant Professor in Mechanical Department from Emmanuel Lesser JJ College of Engineering. Now I am teaching about the subject Process Planning and Cost Estimation. It is understood that the product design for each product has been developed in the design department. To convert the product design into a product, a manufacturing plan is required. The activity of developing such a plan is called process planning. Process planning, also known as operations planning, is the systematic determination of the engineering processes and systems to manufacture a product competitively and economically. Process planning can be defined as an act of preparing a detailed processing documentation for the manufacture of a piece part or assembly. Coming to the contents of this subject, first one is introduction to process planning, second one is methods of process planning, third one is drawing interpretation, fourth one is material evaluation, fifth one is steps in process selection, and final one is production equipment and tooling selection. Coming to the first section, introduction to process planning. What is process planning? The definition of process planning is: the process planning is the systematic determination of the methods by which a product is to be manufactured economically and competitively. It is the link between design and manufacturing, translating design information into a detailed set of manufacturing instructions, as I told earlier. The core purpose of process planning is it bridges the gap between product design, that is CAD or drawing, and actual shop floor production by specifying what operations are needed, in what sequence, on which machines, using which tools, and to what tolerance levels. The scope of process planning covers all planning activities from recipient of product design to delivery of the finished product, including operation planning, tooling selection, setup instructions, quality inspection points, and time or cost estimation. The final output of process planning is the route sheet or process plan, a document that lists each manufacturing operation, the machine equipment to be used, cutting tools, feeds and speeds, setup instructions, and inspection criteria. The objectives and importance of process planning are: first one is reduce manufacturing cost, second one is ensure product quality, third one is minimize lead time, fourth one is optimize resource use, fifth one is enable standardization, sixth one is support cost estimation. Coming to the first one, reduce manufacturing cost. Select the most economical sequence of operations, tooling, and machines to minimize cost per part. Second one is ensure product quality. That means define tolerances, inspection points, and process parameters to consistently meet design specifications. Third one is minimize lead time. Plan efficient process sequences that reduce idle time, setup time, and non-value added operations. Fourth one is optimize resource use. Match operations to available machines and tools for maximum utilization of plant capacity. And fifth one is enable standardization. That means create reusable process plans for similar parts, enabling consistent production across batches. The final one is support cost estimation. That means provide the basis for accurate quotation, scheduling, and production costing. Coming to the next slide, process planning in the manufacturing life cycle. There are 5 manufacturing life cycle are included in process planning process. The first one is product design, second one is process planning, third one is production scheduling, fourth one is shop floor execution, the fifth one is quality inspection. The first step means engineering drawings, CAD models, GD&T specification, and material callouts are designed for a product. Of the first step is product design. Coming to the second step, process planning operation sequences, machine selection, tooling, feeds and speeds setups are included in process planning. The third one is production scheduling, job assignment, machine loading, work orders, timeline planning are included in production scheduling. The fourth one is shop floor execution. In shop floor execution, machining, forming, assembly as per route sheet. The fifth one is quality inspection. The quality inspection is the final part in the manufacturing life cycle of process planning. That means the dimensional checks, surface finish, tolerance verification, etc. are included in the final steps of quality inspection. Coming to the next section, methods of process planning. In this slide, we can see that an overview of process planning methods. The first one is manual process planning, and the second one is variant or retrieval CAPP, that means computer aided process planning. The third one is generative CAPP. The fourth one is hybrid CAPP. The first one means the manual process planning. Experienced process planners manually create route sheets based on knowledge, reference documents and machinability data. And the second one is computer aided process planning based on group technology. That means retrieve or modify existing plans for similar parts. That's why the name called variant or retrieval computer aided process planning. The third one is generative CAPP, that is generative computer aided process planning. Automatically generates a complete process plan from scratch using decision logic, rules and AI algorithms. The final one is hybrid CAPP, that is hybrid computer aided process planning. Combines variant retrieval with generative logic for flexibility and accuracy across diverse part families. Coming to manual process planning and detailed analysis. It involves the characteristics and process and also the advantages and disadvantages. Coming to the characteristics and process, relies on planner's knowledge and experience, uses machinability handbooks and standards. And third one is interprets engineering drawings manually. The fourth one is prepares route sheets, operation sheets, etc. The next one is time consuming but highly flexible. The final one is suitable for job shop environments. Often lacks standardization between planners also. Coming to the advantages and disadvantages. The first one is flexible for unique complex parts. Second one is no software investment needed. The third one is human judgment handles exceptions. The fourth one is suitable for small scale production. But in inconsistency between planners, time consuming and labor intensive, difficult to update and revise plans. That are the disadvantages included. Coming to variant or retrieval CAPP, that is computer aided planning. How it works? Parts coded using group technology, that is GT. GT means group technology. Parts with the similar features share a family code. Then the existing plans retrieved from database, the retrieved plan edited for new parts specifics. Uses optics and my-class coding system. Part families defined by shape, size, tolerance. The database grows richer with each new plan. Coming to the benefits and limitations. The benefits are fast plan generation via retrieval, consistency across similar parts, lower implementation cost than generative CAPP, captures organizational expertise. The limitations included in variant or retrieval CAPP process are only works well within part families, and major edits needed for dissimilar parts. Quality depends on existing database. These three points are the limitations of variant retrieval CAPP process. Coming to generative CAPP, intelligent automated planning. The core concepts of generative CAPP is generates plans from first principles, uses decision trees, rules, and AI or ML. Inputs, CAD geometry, material tolerances. No retrieval of existing plans needed. Process logic stored as knowledge base. Can handle new part geometries. Integrates with CAD CAM systems directly. These are the core concepts of generative CAPP. The applications and challenges included in generative CAPP are: first one is consistent optimized process plans. Second one is handles new or complex parts geometries. Third one is integrates with the SIM and Industry 4.0. Also supports real-time dynamic planning. The challenges included in generative CAPP are: high development cost and complexity, requires detailed knowledge base, difficulty to validate for all cases. Coming to the comparison of process planning methods, first one is manual versus variant versus generative. Manual planning offers maximum flexibility and requires no software, but suffers from inconsistency and high labor cost. It remains valid for unique on-off parts in job shops. And the second one is variant CAPP suitability. Variant CAPP excels in batch production environments where families of similar parts are manufactured repeatedly. The GT coding system is the backbone, that is Optis 9-digit code and MI class 12-digit code are widely used industrial standards. The third one is generative CAPP and Industry 4.0. Generative CAPP is the foundation for all fully automated part manufacturing. Modern systems combine AI, feature recognition from 3D CAD models, and real-time machine availability to auto-generate optimized plans, a critical enabler of digital twin and flexible manufacturing systems. The final one is selection criteria, chosen based on part variety, that is high equal to generative. Production volume means high equal to variant. Budget means low equal to manual, and system integration requirements. Most modern factories use hybrid approaches. Coming to the next section, drawing interpretation. Elements of engineering drawing interpretation includes 6 points or 6 stages. The first one is title block analysis. The second one is orthographic views. The third one is dimensions and tolerances. The fourth one is GD and T symbols. Fifth one is surface finish marks. And sixth one is material and heat treatment. Coming to the first one, title block analysis. Read part-time, drawing number, revision level, material specification, scale, and approval signatures. The second one is orthographic views. Interpret front, top, side views, understand hidden lines, section views, auxiliary views, and projection angles. The third one is dimensions and tolerances. Identify nominal dimensions and bilateral, unilateral tolerances, reference dimensions, and basic dimensions. The fourth one is GD and T symbols. Decode geometric dimensioning symbols include flatness, straightness, circularity, cylindricity, perpendicularity, parallelism, true position, runout. The fifth one is surface finish marks. Interpret raw values, roughness average, RZ values, machining symbols, and lay direction symbols. The sixth one is material and heat treatment. Identify material grade, example ASI 1045, hardness requirements, that means HRC, HB, coating and surface treatment callouts of the different types of materials to identify that the different characteristics and material characteristics of that particular metal or non-metal types of particular product for the final material selection and heat treatment process. Coming to the geometric dimensioning and tolerancing, that is GD&T, form and orientation tolerances. First one is flatness, variation in surface planarity. Straightness means line element deviation. Circularity, it is the roundness of a cross section. Cylindricity means combined roundness plus straightness. Perpendicularity, we also know that 90-degree relationship to datum line. Parallelism means equidistant from datum line. In angularity, specified angle to datum. That means the angularity. Location and runout tolerances include true position, that means location of a future sender, and second one is concentricity, axis to datum axis deviation. The third one is symmetry, equal distribution about median. The fourth one is circular runout, 2D deviation during rotation. The total runout means full 3D surface deviation. Profile of a line means 2D curve tolerance. Profile of a structure means that 3D surface tolerance. Coming to tolerance and surface finish specification. Types of dimensional tolerances include bilateral, unilateral, limit dimensions, fits, ISO tolerances, shaft or hole basis system. In bilateral, plus or minus 0.05 mm, equal both sides are included. In unilateral, plus 0.00 to 0.045 mm one side only. The limit dimensions are 25.00 to 25.05 mm. The fits included clearance, interference and transition. The ISO tolerances include IT grades IT01 to IT180, that is IT01 to IT18. The shaft or hole basis system means that example H7 or G6 etc. Surface finish parameters are RA, that means arithmetic mean roughness, most commonly used. R is at mean roughness depth, peak to valley. R max means maximum profile height. Turned surface RA 1.6 to 6.3 mu meter. Ground surface RA 0.4 to 1.6 mu meter. Lapped or horned RA 0.025 to 0.4 mu meter. Raw costing RA 12.5 to 50, that is 50 mu meter. The systematic drawing interpretation procedures are: first one is review title block, second one is analyze geometry, third one is extract dimensions, fourth one is interpret GD&T, fifth one is note special regs. The first one is review title block, that means confirm drawing number, revision, material, scale, tolerances and approval authority. The second one is analyze the geometry. Analyze the geometry of that material includes study of all views, identify all features, slots, holes, threads, fillets, chamfers, undercuts, etc. The third one is extract dimensions. The extract dimensions means record all nominal sizes and tolerances, identify the critical versus non-critical features. The fourth one is interpret GD&T, identify datums, future control frames and functional geometric requirements. It includes the interpretation of GD&T. The fifth one is note special regs, surface finish hardness, plating, threading, inspection requirements, special notes, etc. That means the special requirements or rigs to identify the development of process called drawing interpretation for the systematic arrangement of procedures for the process planning methods or process planning activities to enhance the product value and the product quality, as well as to got the right way of output as we required. The feature recognition in process planning means, what is feature recognition? Feature recognition is the automated or manual identification of manufacturing relevant geometric entities from engineering drawings or CAD models, such as holes, pockets, slots, threads, chamfers, and undercuts. The importance in process planning are recognized features directly mapped to manufacturing operations. A through hole maps to a drilling operation, a flat surface to milling, a cylindrical bore to boring or reaming. An accurate feature recognition is the foundation for correct operation sequencing. The machining features of taxonomy include prismatic features, which means pockets, slots, steps, bosses, holes. Rotational features include turned diameters, grooves, threads, chamfers. Sheet metal features include bends, holes, notches, flanges. Each feature class has an associated set of feasible manufacturing processes. CAD-based feature recognition include modern CAD system. The software like CATIA, SolidWorks, NX, etc. embedded manufacturing feature recognition tools that can automatically identify machining features from solid models, link them to process plans, and export them to CAM software for tool path generation. Coming to the next section, material evaluation. The material properties relevant to process planning are: first one is machinability, second one is hardness, third one is tensile strength, fourth one is ductility and toughness, fifth one is thermal properties, sixth one is chemical reactivity. The material properties relevant to process planning include these 6 processes or properties of materials to identify the particular characteristics of that material to enhance the required output to get the accurate means of output value of that particular material or particular selected material. The first one is machinability, ease of material removal by cutting to get the required shape and size of the particular material. That means the machinability. It is simply say that to get the required shape and size of the particular material is also known as machinability. So, expressed as percentage related to ASI 1112 steel, that is 100% high machinability equal to lower cost. That means the high machinability is equal to lower cost. We can select the ASI 1112 steel, that is 100%. That means the high machinability. It means the lower cost. The second one is hardness, resistance to surface deformation. The Britnell hardness test, Rockwell hardness test, Vickers hardness test are the mechanical based testing processes. Affects tool selection and cutting parameters. Third one is tensile strength. It means maximum stress before fracture is called as tensile strength simply. Higher strength requires more cutting force, stronger tooling and lower cutting speeds. Ductility and toughness. It means ductile materials such as aluminum, mild steel, etc. produce continuous chips. Brittle materials, that is cast iron, produce discontinuous chips. Coming to the fifth one, thermal properties. Thermal conductivity affects heat dissipation during cutting. Materials with a low conductivity, that is titanium, require generous coolant application. The sixth one is chemical reactivity. Some materials, titanium, stainless, steel react with cutting tool coatings require specific tool grades. It includes carbide, ceramic, CBN, etc. Material families and their manufacturing characteristics include ferrous metals and non-ferrous with special materials. The ferrous metals includes first one is low carbon steel, that is less than or equal to 0.3% C. It is less than or equal to 0.3% of carbon, easily machined, welded. And medium carbon steel, which means 0.3 to 0.6% of carbon, that is tough and heat treatable. The third one is high carbon steel, that means 0.6 to 1.4% of composition or carbon, that means hard or wear resistant. Alloy steel means Cr, Ni, Mo additions for strength, that means the three elements additions for the strength means it means that the additions for strength, that is to make the material strength, we can add alloy steels like chromium, nickel, molybdenum, like that, etc. Stainless steels include corrosion resistant or work hardness. Cast irons means the brittle, excellent vibration damping. Tool steels like HSS, high speed steel D2, H13 for cutting tools. Non-ferrous and special materials include aluminum alloys, light, machinable, good surface finish. Copper alloys means soft, ductile, excellent conductivity. Titanium alloys means a high strength or weight ratio, difficult to machine. Nickel superalloys means inconel, high temperature applications. Plastics means ABS, nylon, PEEK, low cutting forces. Composites means CFRP, GFRP, that is abrasive laminate delamination risk. Ceramics include hard and brittle and require grinding. Definition of machinability. The machinability is the key material of a parameter. The machinability is the ease with which a material can be machined to an acceptable surface finish at lowest cost. It is influenced by cutting tool life, surface quality, achievable cutting forces required, and chip formation behavior. The machinability rating means ASI B112, that is ASI B1112. Free cutting steel is the reference 100%, as I told earlier. Aluminum alloys rate 300 to 1500%, very machinable. Titanium alloys 15 to 4% poor machinability, and stainless steel 40 to 80%. Cast iron include 60 to 80%, hardened steel 5 to 30%. Factors affecting machinability are microstructure, that is fine grained materials machined better. Second one is hardness. Higher hardness reduces tool life. The third one is work hardening tendency. Austenitic stainless steels harden during cutting. Thermal conductivity. Low conductivity causes localized heat. The fifth one is abrasive content. Carbides, oxides wear cutting edges rapidly. Improving machinability. Free machining additives. Sulfur, lead, selenium, bismuth. Improve chip breaking and lubrication at tool workpiece interface. Annealing heat treatments reduce hardness. Proper cutting fluid selection dissipates heat and reduces friction. Coming to the material evaluation criteria for process selection, the technical criteria are mechanical property requirements, that is strength and hardness. As an example, so the surface finish achievability for the material is the second criteria. The third one is tolerance capability with available processes. The fourth one is heat treatment requirements and distortion risk. And next one is weldability, brazability, formability needs. The next one is corrosion wear resistant requirements. Operating temperature range compatibility is the final one. Economic criteria includes raw material cost per kg, commodity price, material availability and lead time, machining time inversely with the machinability, tooling cost and wear rate impact. The fifth one is scrap rate due to material defects. The next one is near net shape potential, reducing machining process, the recyclability and end of life value. The section 5 is steps in process selection. The steps in process selection, a systematic approach, is shown in the figure. The first one is analyze part features, the second one is identify feasible process, third one is evaluate capabilities, fourth one is select and sequence, the final one is validate plan. Coming to the first one, analyze part features. That means identify all geometric features, dimensions, tolerances, surface finish requirements from drawings. Coming to the next one, identify feasible process. List all manufacturing processes capable of producing each feature, that is primary and finishing. The third one is evaluate capabilities. Check process capability, CP, CPK, achievable tolerances and surface finish RA values. The fourth one is select and sequence. Choose processes that meet requirements at minimum cost, arrange in logical machining order. Fifth one is validate plan. Verify sequences for correct datum use, clamp accessibility and production feasibility. Coming to the process capability and tolerance achievability, process versus tolerance table. The first one is sand casting. The sand casting includes plus or minus 0.5 to plus or minus 2.0 mm and RA is 12.5 to 50 mm. In die casting, it is changes to 0. That is plus or minus 0.1 to plus or minus 0.5 mm, RA 1.6 to 6.3 mm. Coming to the turning, that is roughness, plus or minus 0.1 mm, RA 6.3 to 25 mm. Coming to the turning, that is finish, plus or minus 0.025 mm, RA 0.8 to 3.2 mm. Milling, coming to the rough, plus or minus 0.1 mm, RA 3.2 to 12.5 mm. Coming to the milling, the finishing process, plus or minus 0.025 mm, RA 0.8 to 3.2 mm. Grinding fine 0.005 mm, RA 0.1 to 0.8 mm. Coming to the special and precision process, horning includes 0. Plus or minus 0.005 mm, RA 0.025 to 0.4 mm. Lapping plus or minus 0.002 mm, RA 0.012 to 0.1 mm. EDM means plus or minus 0.005 to 0.02 mm, RA 0.4 to 3.2 mm. Laser cutting includes plus or minus 0.05 to 0.1 mm. Broaching includes 0.01 to 0.025 mm, RA 0.8 to 3.2 mm. Framing includes plus or minus 0.005 to 0.025 mm, RA 0.4 to 1.6 mm. Thread cut grinding includes 0 plus or minus 0.005 to 0.01 mm pitch. Operation sequence and rules and best practices include fundamental sequencing principles, that is rough before finish. Remove bulk materials first to reduce cutting forces on subsequent precision operations. Second one is datum surface first. Machine reference surfaces before dependent features. Third one is internal before external. Machine internal features, that is holes, bores before external profiles where possible. The second one is minimize setups. Each setup introduces positioning error and consumes non-productive time. Group operations that use the same datum, fixture or machine orientation. Modern 5-axis machining centers allow multiple phases to be machined in a single setup, dramatically reducing setup count and cumulative error. Coming to the heat treatment sequencing. Place rough machining before heat treatment, cast hardening, quench and temper to remove the majority of material before hardening. retaining distortion allowance. Finish machining, grinding after heat treatment achieves final dimensions and surface finish. The critical sequencing considerations include avoid machining thin-walled sections until late in the sequence to prevent distortion from clamping forces. Drill before ream, rough before finish bore. Avoid creating stress concentrations in semi-finished workpieces, etc. Consider chip flow and coolant. Coming to the key decision factors in process selection. The first one is geometry and feature type. Second one is dimensional tolerance. Third one is surface finish required. Fourth one is production volume. Fifth one is material properties. Sixth one is cost and lead time. The first one is the shape, size and type of feature determines feasible processes. That is, cylindrical is equal to turning grinding, flat is equal to milling or grinding, holes equal to drilling, boring, reaming. That is the geometry and feature type. The second one is dimensional tolerance. Tight tolerances IT6 and below mandate precision processes like grinding, honing or lapping. Coarse tolerances allow turning or milling. The third one is surface finish required. Required RA values drives process choice. RA 0.8 μm needs grinding. RA 3.2 meter is achievable with finish turning. RA 0.05 μm requires lapping. The fourth one is production volume. High volumes favor specialized tooling, transfer lines and automated cells. Low volumes favor flexible CNC machining centers. Fifth one is material properties. Machinability, hardness and thermal properties dictate feasible cutting processes and tool materials needed. Final one is cost and lead time. Unit cost, tooling investment, amortization, machine availability and delivery schedule all influence process selection decisions. The sixth section, that is the next section, production equipment and tooling selection. Types of production equipment are: first one is center lathe and CNC turning centers. Second one is milling machines and machining centers. Next one is drilling and boring machines. Fourth one is grinding machines. Fifth one is EDM and special processes. Sixth one is forming equipment. The first one means center lathe and CNC turning centers. For cylindrical, conical and threaded components, CNC turning centers offer multi-axis capability, leave tooling and sub-spindles for complete part machining. The second one is milling machines and machining centers. Vertical horizontal milling for flat surfaces, pocket slots, contours, 3 to 5 axis CNC machining centers enable complex 3D profiles in one setup. The third one is drilling and boring machines. Radial drilling centers and CNC boring mills for hole making, boring to decision diameters and interpolation milling. The fourth one is grinding machines. Surface cylindrical centerless and internal grinding machines for precision finishing to tight tolerances and fine surface finish. The EDM and special processes include wire EDM, zinc EDM for complex profiles in hard materials, laser cutting, water jet, plasma for profile cutting and heat sensitive materials. The sixth one is forming equipment. Press brakes, stamping presses, forging hammers, rolling mills, extrusion presses for near net shape bulk forming operations. These are the types of production equipment. Machine tool selection criteria includes technical criteria and operational economical criteria. The first one is technical criteria, which includes required machining operations, that is turning, milling, reaming, boring, etc. Workpiece size, weight and envelope, that is XYZ travel, that is direction. Dimensional accuracy and repeatability needed. The next one is surface finish capability of machine. Next one is number of axes required, that is 3 or 4 or 5 axes, etc. Spindle speed, range and power in kilowatt. Rigidity and damping characteristics is the final technical criteria of tool selection. The machine tool selection criteria also includes, as I told earlier, operational and economical criteria. which includes production volume and lot size compatibility, and flexibility for product mix changes, setup time and changeover requirements, automation and pallet robotic loading options, cycle time and throughput rate, capital cost, running cost, ROI analysis, maintenance requirements and availability, etc. are the operational and economical criteria of machine tool selection. Coming to cutting tool materials, that is a selection guide which includes tool material properties and types and cutting tool geometry parameters. In tool material properties and types, HSS, that is high speed steel, tough, regrindable, general use, cement carbide, that is WC or CO, high hardness or wear resistant, coated carbide, TIN, DLC coatings on carbide, ceramic means A203, Si3N4, hardness at high temperature, brittle. CBN means cubic boron nitride for hardened steel greater than 45 HRC. PCD means polycrystalline diamond, non-ferrous and composites. Cement means TIC based, that is titanium carbon based, excellent for finishing stainless. Coming to cutting tool geometry parameters, first one is rack angle, controls chip flow and cutting force direction. Next one is clearance angle, prevents rubbing behind cutting edge. The third one is helix angle, affects chip evacuation in drilling or milling. The next one is nose radius, surface finish and tool strength trade-off. The next one is cutting edge angle, approach angle on turning tools. The next one is land width, edge strength on indexable inserts. Chip breaker geometry controls chip shape and flow. Tooling selection for key manufacturing operations include turning operations, milling operations, drilling operations, boring operations, grinding operations, threading operations. In turning operations, use carbide inserts, that is CNMG, TNMG, VCMT with a grade selection based on work material. Positive rec for aluminium, negative rec for steel, CBN for hardened steel. Second one is milling operations. Face mills with indexable inserts for flat surfaces, solid carbide and mills for pocket slots, high feed mills for rapid stock removal, ball nose for 3D profiles. The third one is drilling operations. HSS CO for general drilling, solid carbide drills for small precise holes, indexable insert drills for large diameter. Use through coolant for deep holes, that is L by D greater than 5. For boring operations, single point boring bars for precision bores, adjustable diameter, high rigidity anti-vibration bars for deep boring, line boring for aligned bore systems. The fifth one is grinding operations. Alumina wheels for steel, that is AI203. Silicon carbide for cast iron and non-ferrous. CBN grinding wheels for hardened steel and super alloys, which means the long wheel life. Threading operations. Tapes for internal threads, hand, machine, foam tapes. Thread milling for difficult materials. Thread grinding for precision. Die heads for external threads in production. Work holding systems and fixture design include common work holding devices and fixture design principles. That is 3-2-1 rule. The 3-jaw self-centering chuck, round bar stock. 4-jaw independent chuck. Irregular shapes. Collar chuck, precision small diameter parts. Face plate, large irregular or asymmetric parts. Next one is tailstock center, support for long workpieces, machine wise, prismatic parts in milling. Magnetic chuck, thin flat parts on grinders. The fixture design principles, that is 3-2-1 rule. 3 points define the primary locating plane, 2 points define secondary or side plane, 1 point defines the tertiary, that is end plane. Minimum clamping folds to prevent movement. Clamp over support points to avoid deflection. Error proof design to prevent misload. Quick change features for reduced setup time. Putting it all together, integrated process plan. The first one is drawing interpretation, extract features, dimensions, GD&T for surface finish and material requirements, etc. The second one is material evaluation, assess machinability, hardness, special requirements and process capability. The third one is process selection, map features to feasible processes, select based on tolerance, finish, volume, cost, etc. The fourth one is equipment selection, choose machines matching part size, operation type, accuracy and production rate. The final one is tooling selection, select cutting tools, insert grades, geometry and work holding for each operation. These are the integrated process planning activities. Putting it all together, we can understand that these 5 elements or 5 stages or 5 planning activities are the main important activities that are putting it all together to got the integrated process plan activities. That is the drawing interpretation, material evaluation, process selection, equipment selection, tooling selection. These 5 stages are the important in integrated process planning activities. Thank you.